Hello everyone. So this is lecture 15 of MA 221, and today we'll be discussing about differential equations. So what are actually differential equations? An equation involving derivatives. So before looking into some examples, just let me classify some types of differential equations. For example, we have first order differential equation where the equation includes first derivative. We denote it by dy over dx or y prime. The second classification might be second order differential equation, which includes second derivative or y double prime. There is third order, which basically includes third derivative y triple prime. And there are others, but these three are like most occurring classifications. Okay, now examples. So the simplest example can be dy dx is same as 5y. We'll solve it later, but the general equation, general solution rather, of this type of differential equation would be of the form y is c to the 5x. Okay, you can check that this equation actually satisfies this differential equation. For example, if you just calculate dy over dx, then you'll get c times 5 into the 5x, right? Which is just 5y. Okay, so therefore, this is actually a solution of the differential equation. Okay, cool. Um, the other type of example can be this y double prime plus 4y is same as 0. This is a second order differential equation, but you will solve it in math 340. This is out of scope right now, but I can just make a comment that this has general solution of the form y to be a sine 2x plus b cosine 2x, like that. And if you wish, you can check y prime and y double prime. You calculate this too. And then if you just add y double prime plus 4y, you will get back 0. So therefore, this is actually, and that way you can just verify that this is actually a solution. Okay, cool. Or let me write it down. It will be 2a cosine 2x minus 2b sine 2x. And there you'll have minus 2a sine 2x minus 4 b cosine 2x. Okay. And basically you can just add y double prime and 4y. You'll get back 0. Okay, cool. Now the next thing that I want to discuss is separable differential equations. Okay. So in this, we will solve first order differential equation of the form dy over dx is fx gy. So basically what this type is, you can separate out x and y as functions. So this type of differential equation has a technique to solve those, and those are called separable differential equations. The name comes from, as we can separate out the x and y part on the right hand side of the differential equation. Okay, so what is the approach to solve it? So eventually, uh, uh, um, so if you write dy over dx as fx over hy, this is equivalent condition. So I can write this fx times gy as fx over hy, right? And then this can be written as hy dy and fx dx on the other hand side. And then basically we will integrate. And by integrating, we'll get solution. Okay. Let's name this star. So what I'm saying is that when you have fx times gy, I can write this as like this, fx over 1 over gy, right? There's no harm. And then I'm renaming this 1 over gy as hy here. Okay. So this is basically, playing with the function. And at the very end, we'll separate out the y part on one side and x part on the other side. And then basically we'll integrate. So the next question might be why star is a solution. Because if I name capital Hy as integration small hy dy and say fx as integration small fx dx, then if I do the, so I can see from star h of y is capital Fx plus c, right? Because I name in that way. And then if I do the, derivative, then Fx is basically df dx, and df dx is same as dh dx, right? So this comes from this line. I can write this, right? And from this line, I can write the other equality, right? But because if I do the derivative here, then I'll get df dx is same as dh dx, right? So that's why I can write the other half of the equality. Okay. Okay, but now what is what is dh dx? I can write this as dh dy and then dy dx, right? There is no harm. But then dh dy is same as small hy and dy dx, right? So therefore, that is same as dy dx is same as, fx over hy, right? And that was our given differential equation. So therefore, what we can say is the star is actually a solution of the differential equation. Okay. Let me solve examples. I guess things will be more clearer. So if I have, say, dy over dx is x squared plus 1 over y squared. So I can see that this right hand side is like separable. So I'll take the y part on one side and x part on the other side, and then do the integration. Y squared dy, x squared plus 1 and dx. Then I'll get y to the third over 3 is same as x to the third over 3 plus x plus c, right? And basically I can just rewrite this as like this, 3x 3c, right? So therefore I get y to be cube root of x to the third plus 3x plus c prime. Okay, this is arbitrary constant, so I can rewrite this as c prime. This is possible. Okay, so this is my general solution. You can write 3c here as well, no problem, but generally people just write one, constant c prime or like something in that place. Okay, let me solve one more problem. See, if I have dy dx same as x squared y plus 1, then I'll get 1 over y plus 1 dy to be x squared dx. Then this is ln, if I do the integration now on both sides, I'll get ln y plus 1 is same as x to the 3 over 3 plus c. Okay. Now, this is same as y plus 1 e to the x to the 3 over 3 plus c, right? We know that e to the x is always bigger than 0. So therefore, this modulus can be removed and we can write y plus 1 is same as e to the x to the 3 over 3 times e to the c, right? Or, no. If I remove the modulus sign there, I should write plus or minus there, right? Because from this line, if I take positive or negative, doesn't matter. From the previous line, if I go from like last line to the previous line and I take the modulus, I'll get back the previous line. So therefore, I should write plus or minus there to justify the last line and the previous last line is same. Okay, so this is y plus 1, and now e to the x to the third over 3 is there. But again, this plus or minus e to the c, this part is again anyway a constant, right? So I can write this as just c prime. Okay, cool. So therefore, my final solution is c prime x to the e to the x to the third over 3 minus 1. This is my final solution. Okay, cool. The next problem that I want to discuss is um, this problem. Oh, just wait a minute. Okay, let me solve the next problem. Say the question is now given like this: 1 plus t square dy over dt. Here the x is replaced by t, the independent variable. So say I have this differential equation, and with one more condition, that when my t is 1. So this is basically saying that when my t is 1, my y is 0. Okay. So let me first solve the differential equation to get the general solution, and then we will see what is a particular solution or whatever. So this is minus t e to the y. Okay, I just shift the t e to the y on the other side, and then the idea is still the same. I'll try to collect all the uh, t term on one side. So say minus t over 1 plus t square dt is there, and there is e to the y as well. But then e to the y should not be on the right side, it should be on the left hand side. So I'll collect the minus e to the minus y dy on the left hand side. On the right, I should have t over 1 plus t square dt. Okay, cool. Now I can see that I have y term on the left hand side and t term on the right. So therefore, I can do the integration now. This will give me just e to the minus y. And on the other side, I'll get half ln 1 plus t square plus c. Okay, I can take the modulus there, no harm. But this is my general solution. Why this is called general solution? Because this c can be any number. Okay, it can be any constant. But I have one more constraint, right? Y at 1 is 0. So now I'll use that. So use t equal to 1 and y equal to 0. Then, so I'll put t as 1 everywhere in there. So therefore, I can see that is half ln 1 plus 1 square plus c is there. And I know that y is 0, so therefore I'll get e to the minus 0 on the left hand side. This is 1 on the left. On the right, I have half ln 2 plus c. So therefore, my c will be 1 minus half ln 2, right? So therefore, my particular solution with respect to the constraint y at 0 is 1 will be e to the minus y, same as half ln 1 plus t square, and c will be replaced by 1 minus half ln 2. Okay, as I got the c to be this. Okay, cool. So now I have minus y is ln of the whole quantity there, which is half ln 1 plus t square plus 1 minus half ln 2. Okay, and then therefore y will be just minus ln half ln 1 plus t square plus 1 minus half ln 2. Okay, and this is the solution. So therefore, sometimes the differential equation has like a weird looking solution, but that's fine. Okay, now I'll talk a little bit about different type of growths. So say exponential growth. Um, so when my rate of growth or say decay is proportional to the amount of the quantity present, then the growth the then the growth is called exponential growth. So for example, say dy dt is ky, where k is a constant of proportionality. Okay. So when I have this type of differential equation, then we call that the growth is exponential. Okay. So for example, in various population model, the growth usually is exponential growth. Yeah, and also say I give this example. Say I have a population growth of say Chicago is given as dp dt is kp, where pt is the population at time t and p0 is the initial um, population. Okay, then this type of growth is also exponential. Why the name exponential is there? If you solve it, you will get the answer. Okay, so let me give one more example, and then we can solve one example. We can solve one problem. Say another example can be like this: radioactive decay. So in physics, if you try to solve uh, you will try if you try to get the differential equation for a radioactive decay, most of the time you'll get this dA over dt is minus Ka, where At is the amount left after T days, amount of a radioactive particle, and A naught is the initial amount. Okay. And the question is why we get the name exponential growth or decay, because if you solve this, you'll get the the answers or the general solution as p naught e to the kt for the population, and for the radioactive decay you'll get like a naught e to the minus kt. So the exponential term is coming in the general solution, so therefore we call this type of growth or decay as exponential growth or decay. Okay, cool. Let me solve one example for you. Okay, so say my example is something like this. Solve the differential equation. This is abbreviation for my differential equation. Dy dt is lambda y, where y at 0 is y naught. At the initial time, my y is just y naught. So therefore, this is also a separable type of differential equation. So I can write y on one side and then the t part on the other side. and then do the integration, I'll get ln y is same as right, modulus of y doesn't matter, lambda t plus c, right? In other words, I'll get modulus y to be e to the lambda t plus c, and this is e to the lambda t times e to the c. Okay, so far so good. Now, if I remove the modulus, I'll get plus or minus e to the c times e to the lambda t. But again, this is a constant, so I can write this as c prime e to the lambda t y. So again, this is general solution. Okay, but I have one more constraint there. So therefore, I should get the particular solution. When I have one or more constraint given in the problem of a differential equation, my solution should be a particular solution. So I know that at t equal to 0, my y is what? Y is y naught. So if I put t equal to 0, I'll get c prime e to the 0 as this. So therefore, my c prime is basically y naught. So therefore, a particular solution will be y is y naught e to the lambda t. Okay. Okay. Sweet. Okay. Now, now let me solve one more of this type of differential equation. So say my problem in this case is given as solve the logistic equation as dp over dt is same as k times p1 minus p over x, and the initial condition is like this: p at 0 is p naught. Okay, but then this can be written as, oh, okay, this is actually lambda. Yeah. Okay, I can rewrite this as k over lambda, and then p p. Okay, I can take the lambda 1 over lambda factored out, then I'll get that, and then I can write this as k over minus k over lambda p times p minus lambda. Okay, why you'll see later why I have done this. But then I can separate out the p part on the left hand side and the rest of it on the right hand side, like this, and then do the integration. Now for the integration, this is quite, you should recognize this thing. Okay, this is sort of a partial fraction type of problem. So I'll do it directly. I can write this as, 1 over p, 1 over p minus lambda minus 1 over p, like this. So if I do the calculation, it should be, yeah. So if I do the calculation there, this is nothing but p times p minus lambda there, and then p minus p plus lambda. Okay, so lambda over that. But then in this line on top there is 1, but I can rewrite this line as like this. I can push this lambda there, then I'll get lambda there, and there will be no lambda here, right? Same thing. Then these two lines are exactly equal, right? This line and this line is identical, just doing some geometry. Sweet. So, and now I can just basically do the integration. I'll get ln p minus lambda minus ln p. I'm not writing the modulus there inside ln because it will not, I mean, there is no need because anyway I'll get like plus or minus just like the previous problem, and then that will be just a arbitrary constant. So I'm not bothered about the modulus anymore. So this is minus kt plus c, but then this I can write as by the law of logarithm p minus lambda over p is minus kt plus c. And now this is p minus lambda over p is same as e to the minus kt plus c. But then this is e to the minus kt times e to the c is same as, I can write this as 1 minus lambda over p, right? This can be written as this, right? And then this is nothing but 1 minus lambda over p is c prime e to the minus kt. Okay, cool. But then this is just, you can just write this in terms of p on the left hand side. So I'll get c prime e to the minus kt minus 1, and then over p is just, 1 minus c prime e to the minus kt. This is basically algebraic manipulation, nothing else. And the NP will be like lambda over 1 minus c prime e to the minus kt. Okay. But again, this is general solution. I need to use the extra condition given, which is this p at 0 is p naught, to get the particular solution. So I'll leave the final solution for you, but the answer should be like this: 1 minus lambda p naught e to the minus kt. Okay. You can figure it out how. Okay. The next thing that I want to say is Newton's cooling law. Okay. What does it say? It says that the rate at which uh, uh, the temperature of a heated body um, cools is proportional to the difference between the temperature of the object and the surrounding temperature. Okay, what does it mean? It basically mean if Tt is capital T of T is the temperature of the object, and Tr is the room temperature. Say Tr is the room temperature. Then the temperature of the object obeys this differential equation. Okay, where K is a constant less than 0 most of the time. Okay. Before solving one problem, I just want to, you know, give some more idea of what's going on. So what does the graph look like? Graph of temperature T. So say this is just a, so this is the room temperature Tr, which is a constant, just for the sake of simplicity. And say at initial time, the temperature of the object was T naught here, higher than the room temperature. Then basically what does the equation says, if you solve the equation, you will get a solution which kind of decays as the time approaches towards infinity. So which actually obeys the general physical law. If you have a object hotter than the room temperature and you keep that object for some time, you'll see that the temperature of the object will just try to reduce down to the room temperature. So it kind of makes sense. And on the other hand, if the temperature of the object is like below the room temperature, say T naught is here, then you can expect what will happen in that case. It will like try to increase the temperature of the object near to the room temperature. Okay, cool. Let me solve one problem on this regard. Before that, let me just clear down things. So, say my example is like this. A 90 degrees Celsius cup of coffee um, is placed in a 20 degrees Celsius room. So maybe the person is Asian because this is like in degrees Celsius. So say after 10 minutes, it has cooled to say 48 degrees Celsius. When was it at 65 degrees Celsius? So the question is like, you have a cup of coffee. Initially, it was 90 degrees Celsius. And after 10 minutes, the temperature of the coffee is like 48 degrees Celsius. The question is at what time it was at 65 degrees Celsius. So we have to use Newton's law here. So which is this. This 20 is the initial the room temperature, sorry. So now if I try to solve it, then what will I get? So dt over t minus 20 is k dt, right? Separable, the same idea. Then integrate it to get ln t minus 20. Again, I'm avoiding the modulus to get this. And then this is t minus 20 is same as e to the kt plus c, which is e to the kt times e to the c, which is just c prime e to the kt plus 20. T is same as this. And then I know that the temperature initially was 90, right? So T of 0 is 90. So therefore, 90 is same as C prime e to the 0 plus 20. So C prime is 70. Okay, cool. So therefore, my equation of the temperature of the object is T of T is 70 e to the kt plus 20. Okay, cool. So, but what else do I know? The one more information that I have not used so far is this. After 10 minutes, it was cooled down to 48 degrees Celsius. So when my time t is 10, okay, then my temperature was 48 degrees Celsius. Okay. So if I use this, I'll find the constant k, right? So from this, I can say that 48 is same as 70 e to the k times 10 plus 20. In other words, 28 is same as 70 e to the 10k. And then this is just 28 over 70 is e to the 10k. Or this is basically, so 10k is ln 28 over 70. So k is 1 over 10 ln 28 over 70, right? Okay, so therefore my equation now becomes, I know what k is as well, 20 plus 70 e to the 1 over 10 ln 28 over 70 times t. Okay, now the question was, what is when, okay, sorry, not what, when temperature is 65. Okay, that was the question. So for that, I'll just replace capital T with 65, and then I'll try to find what is my temperature should be. Sorry, my time should be. I have to find the small t from there. Okay, it's not too difficult. It will be 45 over 70 is same as e to the 1 over 10 ln 28 over 70 times t. And the rest is basically algebraic manipulation. So ln 45 over 70 will be 1/10 ln 28 over 70 times t. Then cross multiply to get 10 ln 45 over 70 times, or rather, I'll just write it down. And ln 28 over 70 is my t. So if you put that in calculator, you'll get your t as 4.82 minutes. And that is your answer basically. Okay. So after like approximately like 5 minutes, your temperature of the coffee will be 65 degrees Celsius. Okay. So one thing maybe I just assume that you know how to deal with this type of equation. When you have e to the something and you need to get the value for, you need to solve for this small t, then what you do is you take ln both side, and then this ln and e sort of like reverse sort of thing, inverse sort of thing, so this will go away and you will get ln of 45/70 on the left hand side, and right hand side you will get the power of e to the t. That is the basic idea that I've used. So this is it regarding differential equation, and I hope you'll be able to solve the homework problems. But if you struggle with any of those, you are welcome to meet me in the office hours. Okay, thank you.